In this video, we are going to learn about number 1, one of the most interesting triangular array of numbers known as the Pascal's triangle, which is named after the famous French mathematician Blaise Pascal. Number 2, the different patterns of numbers inside the Pascal's triangle. And number 3, the uses of the Pascal's triangle. Let's start with learning how to build the Pascal's triangle. Start with writing 1 on the top. Then write 2 ones in the next row to make a triangular pattern. Extend the pattern writing ones diagonally. Fill the space by writing the sum of 2 numbers above that space. That is, add these 2 numbers and write the sum here. Continue the procedure. That is, extend the pattern by writing ones diagonally. Add these 2 numbers and write the sum here. Add these 2 numbers and write the sum here. Extend the pattern further. Add these 2 numbers and write the sum here. Add these 2 numbers and write the sum here. Add these 2 numbers and write the sum here. We can extend this pattern forever, but I'm going to add 2 more rows. So, we have got a triangular pattern of numbers that is called as the Pascal's triangle. Let's observe the beautiful patterns of numbers in the Pascal's triangle now. Start observing patterns of numbers diagonally. In the first diagonal on the left hand side, there are all ones. Similarly, in the first diagonal on the right hand side, there are the ones also. In the second diagonal on the left hand side, there are the counting numbers. Similarly, in the second diagonal on the right hand side, there are the counting numbers also. In the third diagonal on the left hand side, there are the triangular numbers. Similarly, in the third diagonal on the right hand side, there are the triangular numbers also. In the fourth diagonal on the left hand side, there are the tetrahedral numbers. Similarly, in the fourth diagonal on the right hand side, there are the tetrahedral numbers also. Let's know one more beautiful characteristic of the Pascal's triangle. The Pascal's triangle is symmetrical about this vertical axis. That is, its left and right half sides are mirror images of each other. Let's move to the next pattern of numbers in the Pascal's triangle. Horizontal sums. The horizontal sums of numbers in the Pascal triangle have a very special pattern inside. That is, the sum of numbers in each row is double than the sum of numbers in the previous row. In the first row, we have only a single number, that is 1. In the second row, we have 2 numbers, both are 1s, and the sum of these numbers is 2, which is double than 1. In the next row, we have 3 numbers whose sum is 4, which is double than 2. In the next row, we have 4 numbers whose sum is 8, which is double than 4. In the next row, we have 5 numbers whose sum is 16, which is double than 8. In the next row, we have 6 numbers whose sum is 32, which is double than 16. And in the next row, there are 7 numbers whose sum is 64, which is double than 32. Note that these sums are powers of 2's. 1 is 0 power of 2, 2 is 1 power of 2, 4 is 2 power of 2, 8 is 3 power of 2, 16 is 4 power of 2, 32 is 5 power of 2, and 64 is 6 power of 2. Let's move to the next pattern now. Powers of 11. The numbers in the rows are powers of 11. We know 0 power of 11 is 1, and here is the number 1. 1 power of 11 is 11, and here is the number 11. 2 power of 11 is 121, and here is the number 121. 3 power of 11 is 1331, and here is the number 1331. 4 power of 11 is equal to 14641, and here is the number 14641. 5 power of 11 is 161051, but this number is different. But don't get worried. Actually, the digits are overlapped like this. 5 and 1 are overlapped to make 6. Similarly, 0 and 1 are overlapped to make 1. 6 power of 11 is 1771,561, and this number is different, but we can have the actual number by using the same technique stated above. And here comes the next pattern. Squares of numbers in the second diagonal. The square of a number in the second diagonal is equal to the sum of the number next to it and the number below the both. For example, this number 2 lies in the second diagonal. Its square is equal to sum of these two numbers. That is, square of 2 is equal to 1 plus 3. Similarly, this number 3 lies in the second diagonal as well. Its square is equal to sum of these two numbers. That is, square of 3 is equal to 3 plus 6. Similarly, square of 4 is equal to sum of these two numbers. That is, 4 square is equal to 6 plus 10. Similarly, square of 5 is equal to sum of these two numbers. That is, 5 square is equal to 10 plus 15. And here is the next pattern that is amazingly beautiful. It is about Fibonacci sequence. What is Fibonacci sequence? The Fibonacci sequence is a sequence that starts with 0 and 1, and then every next number is the sum of previous two numbers. That is 0, 1, 1, 2, 3, 5, 8, 13, so on is the Fibonacci sequence. Note that first two numbers are 0 and 1. Next number 1 is the sum of previous two numbers 0 and 1. Next number 2 is the sum of previous two numbers 1 and 1. Next number 3 is the sum of previous two numbers 1 and 2. Similarly, 5 is the sum of 2 and 3. 8 is the sum of 5 and 3. And 13 is the sum of 5 and 8. Now, observe this orientation of lines in the Pascal triangle. On the first line, there is only a single number, that is 1. On the second line, there is only a single number, that is again the 1. On the next line, there are two numbers, both are 1s. On the next row, there are two numbers. First one is 1 and the second one is 2. On the next row, there are three numbers, 1, 3 and 1. On the next line, there are three numbers, 1, 4 and 3. On the next line, there are four numbers, 1, 5, 6 and 1. On the first line, there is only single number, which is 1. On the second line, there is again single number, which is 1. But on the third line, there are two numbers whose sum is 2. And sum of these two numbers is 3. Sum of these numbers is 5. Sum of these numbers is 8. and sum of these numbers is 13. Note that all these numbers are element of the Fibonacci sequence except the 0 in the start. Let's observe one more pattern. It's about Sharpinsky triangle. What is Sharpinsky triangle? The Sharpinsky triangle is a triangle that contains an ever-repeating pattern of triangles. For example, draw a triangle. Draw another triangle inside it whose vertices touch the midpoint of the side of the first triangle, and repeat the procedure by drawing more triangle inside. In this way we get an ever-repeating pattern of triangles which is known as Sharpinsky triangle. Now, if we color differently even and odd numbers in the Pascal triangle, then we get a triangle which resembles with Sharpinsky triangle. And here is one more interesting and important thing about the Pascal's triangle that describes a unique pattern inside the Pascal's triangle. Here is the Pascal triangle, and here comes another triangle. Let's establish one-to-one correspondence between both the triangles. That is, compare this number 1 with this combination 0 combination 0. If we simplify the combination 0, we get 1. So both these elements are equal. Similarly, compare this number 2 with this combination 2 combination 1. If we simplify combination 2 combination 1, we get 1. So both these numbers are again the same. Similar relation can be proved between the corresponding elements of both the triangles. Let's conclude something. Pascal's triangle is also an n-choose k triangle. It helps us in choosing a certain number of combinations from a given number of choices. Let's learn about the uses of the Pascal's triangle now. Here comes the use number 1. Heads and tails. The Pascal's triangle can help us in finding how many ways heads and tails can combine. For example, if we toss a coin once, the probability of getting head is 1 and the probability of getting tail is also 1. If we toss that coin twice, then the probability of getting 2 heads is 1. The probability of getting 1 head and 1 tail is 2, and the probability of getting 2 tails is 1. If we toss that coin thrice, then probability of getting 3 heads is 1. The probability of getting 2 heads and 1 tail is 3. The probability of getting 1 head and 2 tails is again 3. And probability of getting 3 tails is 1. In the Pascal triangle, these numbers tells us that if we toss a coin once, then the probability of getting head is 1, and similarly the probability of getting tail is also 1. These numbers in the Pascal triangle tells us about when we toss a coin twice that the probability of getting 2 heads is 1, the probability of getting a head and a tail is 2, and the probability of getting 2 tails is 1. Similarly, these numbers tells us if we toss a coin thrice, then probability of getting 3 heads is 1. The probability of getting 2 heads and a tail is 3. The probability of getting one head and two tails is 3, and probability of getting three tails is 1. Let's know about the next use of the Pascal's triangle. Combinations. The Pascal's triangle can help us in finding a certain number of combinations from a given number of choices. For example, if we have to choose 2 balls from a box that contains 4 balls, we can determine the number of combinations using the Pascal's triangle. How? We know the Pascal's triangle is an n choose k triangle. This number 1 is equivalent to combination 0, combination 0. These numbers are equivalent to combinations 1, combination 0 and 1, combination 1. These numbers are equivalent to combinations 2, combination 0, 2, combination 1 and 2, combination 2. These numbers are equivalent to combinations 3, combination 0, 3, combination 1, 3, combination 2, 3, combination 3. These numbers are equivalent to combinations 4, combination 0, 4, combination 1, 4, combination 2, 4, combination 3 and 4, combination 4. These numbers are equivalent to the combinations 5, combination 0, 5, combination 1, 5, combination 2, 5, combination 3, 5, combination 4 and 5, combination 5. And these numbers are equivalent to the combinations 6, combination 0, 6, combination 1, 6, combination 2, 6, combination 3, 6, combination 4, 6, combination 5 and 6, combination 6. As we have to choose 2 balls from a box that contains 4 balls, so this combination will tell us the answer of our question, that is 6. So we can have 6 combinations if we choose 2 balls from a box that contains 4 balls. And here is the next and most important use of the Pascal's triangle. It tells us about binomial coefficients. We know a plus b whole power 0 is 1, a plus b whole power 1 is a plus b, a plus b whole square is a square plus 2ab plus b square, a plus b whole cube is a cube plus 3a square b plus 3ab square plus b cube, and a plus b whole power 4 is equal to a power 4 plus 4a cube b plus 6a square b square plus 4ab cube plus b cube. Note that the expansion of a plus b whole power 0 is equal to 1. It has only a single term. The expansion of a plus b whole power 1 is equal to a plus b. It has 2 terms and the coefficients of these terms are 1 and 1. In the expansion of a plus b whole power 2, we have 3 terms whose coefficients are 1, 2 and 1. In the expansion of a plus b whole cube, we have 4 terms and the coefficients of these terms are 1, 3, 3 and 1. In the expansion of a plus b whole power 4, we have 5 terms whose coefficients are 1, 4, 6, 4 and 1. In the Pascal triangle, this number is the coefficient of the terms in the expansion of a plus b whole power 0. These numbers are the coefficients of terms in the expansion of a plus b whole power 1. These numbers are the coefficients of the terms in the expansion of a plus b whole power 2. These numbers are the coefficients of terms in the expansion of a plus b whole power 3, and these numbers are the coefficients of terms in the expansion of a plus b whole power 4. So if we expand the binomial a plus b whole power 5, the number of terms in the expansion are 6 and the coefficients are 1, 5, 10, 10, 5 and 1. and these numbers lie here in the Pascal's triangle. And this is the end of this video. Thank you for being with me. Stay happy. Goodbye.